Now we're going to move on and just talk about CFTs in D equals 2, and we'll be able to compute many more things. So specifically, to answer a question that Hiroshi asked, in the 2D case, we can take a limit of a light cone OPE limit of the 4-point correlator, where we send z bar to 0 in this correlation function. And we see that any operator we exchange between heavy and light contributes z to the h, z bar to the h bar. And so in this light cone OPE limit, we only keep the smallest anti-holomorphic dimensions, or in other words, we only keep the operators with minimal twist in this correlator. The operators with minimal twist in 2D CFTs are the vacuum and the descendants of the vacuum and conserved currents. So if we're studying a CFT that doesn't have... Good. So, so the contribution to a correlator like this of some operator with some dimension h in h bar in the OPE limit of z and z bar small contributes as z to the h, z bar to the h bar. So the dimension of this operator, delta, is h plus h bar, and the spin is h minus h bar. So in other words, operators of minimal twist, where h bar or h is 0, are the only ones that contribute in this particular light cone OPE limit. If z bar goes to 0 with z fixed. Yeah.
H is not 0, okay.
Yeah.
Z is not 0.
Yeah, z is fixed and just z bar goes to 0. It's an asymmetric limit. Yeah. So this is a limit where we're in a Euclidean region, but we're approaching the light cone. And that means that the only contributions that survive are those with minimal h bar because we're sending z bar to 0.
So only h integer, for example, contributes?
So only h integer contributes, yeah.
It doesn't necessarily mean Virasoro descendant.
It doesn't necessarily mean Virasoro descendant.
There are no other chiral operators.
Exactly. So I'm going to.
So are you claiming that you're assuming that only states which have h integer are the descendants of Virasoro?
H bar 0.
So the only states with h bar 0 are conserved currents of some kind, or descendants, in a generalized sense.
They don't have to be current in the usual sense.
Yeah.
Chiral operator. W algebra.
But they're not currents in the usual sense of conserved currents.
Yeah. So I'm going to only compute and assume that the only operators I have with twist 0 are Virasoro descendants of the identity.
Wow, that's a strong state. That's a strong assumption.
Why is that strong?
Sorry, which why is it a strong?
The algebra says the Virasoro algebra.
Yeah.
That's a strong assumption, I'm saying.
Okay. I mean, so in general, it might be possible to compute the contributions of of a doubly algebra. In fact, other people have generalized this to do that, but that's all I'm going to be talking about. So this is dual to a situation in ADS where I only have gravity as a gauge field in ADS.
So just say why I'm finding this a bit strange.
Okay.
I think that just maybe I'm missing something.
Well, it's
Let me see why I'm finding this bizarre. Take the symmetric products of K3 and compute the elliptic genus, right?
Okay.
Only the left movers which are all holomorphic kind of things. So just similar to what you're saying, but Virasoro is a bare part of it.
Yeah. So
what do you mean that just Virasoro? Is it just Virasoro center charge one contribution of infinity out there?
For elliptic genus, h equal 1/2 states also contribute, for example. So it's not h bar,
That's
only
right. So
h bar equals 0 state.
No, I'm talking about the Ramon sector.
You have to think in a short set.
I know. I'm just trying to give an example.
yeah.
Yeah, but this is NS sector.
This is the NS set. So in that case, only
The only
super
vacuum
Virasoro
is h bar equals 0. There's only one kind of vacuum.
No. In these theories with the 2,2 supersymmetry, there's 0,2 chiral algebras always, much more than Virasoro.
No, not in the short
No,
set.
not in NS sector.
No, the chiral algebras. If you take 2,2, there's a chiral. If you take a chiral algebra for 0,2 theories, I'm talking about, Just look at the right supersymmetric but left arbitrary. They form a chiral algebra always. So for any n equal to 0, 2 theory.
But that's not the vacuum set rule.
Yeah,
You have
you
twisted.
twist it, and your h is up to h minus 2q. That's right.
I'm not twisting it. I'm talking about chiral operator. I'm looking at operator.
Okay, so whether it's a strong assumption or not, it's an assumption that I'm going to make. I'm motivated by ADS, and so I'm going to be working. I'm just studying CFTs at large central charge, and I'm only going to be computing the contributions of Virasoro. I'm going to assume that those are the only twisted zero. Generalizing to supersymmetric theories or theories with some W algebra symmetry, I think is very interesting. Some of that W algebra symmetry work has actually been done, but this is the context that I'll be working in. So I'm going to compute the exchange of the stress tensor and all multi-stress tensor states in the 2D CFT. This is supposed to be dual to the exchange of any number of gravitons in ADS3. And I'll do the computation in two ways. So I won't have time to go into detail, and I might stop because of lunch. But I know of three derivations of this formula. The two that I think are most physical and nicest, one I'll call the amplitude method. And for this, we will literally, by brute force, perform the sum on all possible Virasoro descendants of the vacuum being exchanged between the heavy and light operator. Those Virasoro descendants are our gravitons. And it turns out a large number of beautiful simplifications happen. I call it the amplitude method because it's a situation where you're in some sense computing the ADS CFT version of an on-shell amplitude, and the result is much, much simpler than the individual terms that go into it. And the second method is a sort of background field method. So the idea of this method is to perform a conformal transformation in the conformal field theory that greatly simplifies the correlation functions of the stress tensor with the heavy operator. And after you transform to this new background, the computation becomes vastly simpler. In fact, the new background already encodes this sort of Euclidean time periodicity that you expect from the answer, and everything becomes simplest. This is the, I think, best method. This gives the most general results. It's possible to systematically use this to compute 1/c corrections. This gives any Virasoro conformal block exchange between these heavy and light operators. This method is cuter, and it's a nice warm-up, so I'll start with that and hopefully at least be able to say something about this. And just to set expectations, expressed in terms of C and H heavy, the temperature, the Hawking temperature of a BTZ black hole expressed in terms of H and C is this formula. In ADS3, there are two regimes given by the sign of what's under the square root. In one regime, you have a deficit angle in ADS3 and no temperature. And for H over C bigger than a 24th, you have this regime where you have a BTZ black hole with this temperature. And we'll see how this comes out of either of these calculations. OK, so we want to start out with this amplitude method. We want to sum up all stress tensor exchanges. So in 2D CFTs, as probably everyone knows, the stress tensor splits up into a holomorphic and anti-holomorphic piece. I'll remind you that the OPE of the holomorphic piece of the stress tensor has singular terms that look like this. And I mention that just because the Virasoro algebra when we expand T of Z in modes, can be derived entirely from the singular terms in this OPE. And in particular, even if we perform some very complicated conformal transformation to a new coordinate system, then the singular terms in this OPE are conformally invariant, and we get the same Virasoro algebra that will be relevant for our second method. OK, so this is the Virasoro algebra for the modes of the stress tensor. As Hiroshi mentioned, L plus or minus 1 and L0 are the global conformal generators, and they annihilate the vacuum. However, L minus n with n bigger than or equal to 2 don't annihilate the vacuum. They create quote-unquote gravitons. I just use that terminology because the stress tensor acting on the vacuum in the CFT creates something like a graviton in ADS. And so these are our graviton states. So what I'm first going to focus on is just what you'd call the vacuum Virasoro block, which are this exchange between the heavy and light operator of all states that are Virasoro descendants of the vacuum. So in other words, a pure gravitational field. So notice that at large central charge, where we'll be working, at large central charge, you might renormalize the L's and ignore this term. If you were to do that, you just see that the L's are independent harmonic oscillators. So at very, very large central charge, all we're doing is exchanging a bunch of free harmonic oscillator states. So there's a basis which is not orthonormal, which is just L minus A1 through L minus AK acting on the vacuum where all these AIs are bigger than or equal to 2. This is a basis for all of the Virasoro descendants of the vacuum. And a problem that we'll have, that we'll confront in a second, is they're not orthonormal. But for just a moment, schematically, you might imagine that at large central charge, it's reasonable to write the Virasoro vacuum block that we're interested in as O heavy with a sum over all of these AIs divided by some norm. So this is just a starting point. It's not good enough. It's not the correct formula, the order that we'll be working, but it's almost correct. And it has several ingredients that we want to look at. So we see that the numerator is given by these L's acting on O light, these L's acting on O heavy, and some normalization. So the normalization of LA L minus A is just C over 12 A times A squared minus 1, just directly from the Virasoro algebra. And so we see, crucially, that if there are k of these guys downstairs, this is of order c to the k. So at large central charge, this is a large number suppressing this correlation function. However, we want to work in the heavy-light limit, where H heavy is of order c. And similarly, the word identity for the stress tensor tells us that when L's act on O heavy, we get terms of order H heavy to the k. And finally, all of the z dependence is here. The z dependence when we act with L's on O light, we just find z to the 2 H light for the disconnected piece plus the sum of these AIs. So this is what, very roughly speaking, this exchange of all of the gravitons looks like, we have some normalization factor, which is of order c to the k, and we have powers of h heavy coming upstairs with some kinematic factors, and we get all of our z dependence, which is just given by the sum of these labels, which is the total holomorphic dimension. So those are the three ingredients here. Now, I said that this wasn't good enough. The problem is that these aren't actually an orthonormal basis of states. I'm not worrying about
Greater than 1. What is
C is bigger than 1. I'm not worrying about null states. Yeah. So it turns out that, OK, so why are these not sufficiently orthonormal? Well, as an example, if I have L minus A, L minus B, this isn't orthogonal to L A plus B. And so this is of order C. And so in particular, at the level of two of these guys, this object isn't sufficiently orthonormal.
Why do you care whether it is a complete basis, right? Because there are no null states. So why do I care whether I'm using an orthonormal basis? I can use any basis I want to expand.
You can use any basis you want, but you need to.
This is a basis, right?
This is a basis, but you need to write a projector where you exchange all the states with the correct normalization. Yeah.
But you could do that in a non-orthonormal basis. I mean,
good. So, but now, yeah. So then there would have to be an appropriate, very complicated matrix. So I'm going to skip a bunch of steps in a moment. But what I'm basically going to tell you is that if you take into account that you need this orthonormal basis, something very nice happens. So I'm just going to give you an example here, which is just that I have to replace, if I can use this basis, it's actually good enough everywhere but here, it turns out. And you can see that because so L minus A, L minus B isn't orthogonal to this, basically this 2 graviton state and this 1 graviton state aren't orthogonal, but I can orthogonalize I can just use Gram-Schmidt orthonormalization, and I can define some operator x, a, b for 2 graviton states, which is sufficiently orthogonal to the 1 graviton states. And I can keep doing this using Gram-Schmidt to define some x, a1 through ak operators just via Gram-Schmidt that are sufficiently orthonormal.
Doesn't make sense. Oh, no, it makes sense.
OK. So I have 11 minutes before lunch. So there are going to be a lot of results jumping out of hats. But if you work out the contribution of these orthonormalized states, it turns out that they can be rewritten according to a sum of diagrams obeying some simple on-shell diagrammatic rule. And I say on-shell because these are all physical on-shell states in the CFT. So it turns out that this entire V of z is a sum of diagrams with simple diagrammatic rules. So in fact, it's the exponential of a sum of diagrams. So if I draw diagrams where I have a heavy guy and a light guy, these are made up Virasoro rule diagrams, where I attach lines, any number of lines to the heavy guy, and feeding down to one line attached to the light operator. And I label these with these A's that are labeling these Virasoro generators, or these X's. then the diagrammatic rule is simply that I only include 3-point vertices. Propagators are 1 over a plus 1. So for example, this propagator combines a1 and a2, so it's 1 over a1 plus a2 plus 1. There's a notion of momentum conservation. This is 1 over a1 plus a2 plus a3 plus 1. And those are the rules. This diagram is accompanied by a factor of z to the a1 plus a2 plus a3, exactly according to this. And the rules of the game are sum over all diagrams, and then sum over all values of these AIs. So this entire result is just a sum of all of those things. Now, that sounds like it's still very, very daunting. You have to sum to all orders, and you have to sum over the A's. So how is that possible? It turns out that there's a simple recursion relation that this object satisfies. So
I guess aren't there still some powers of c and z to the h?
good. So this is accompanied by this diagram is also accompanied by a factor of 6h over c to the k, and it's also accompanied by an extra kinematic factor of the product of the AIs minus 1 divided by the sum of the AIs.
What about the HL?
This is just a single factor of HL. So I'm making a huge leap here. This is just the sum of all the, the final answer is the exponential of the sum of all these diagrams. So they exponentiate, and we only get, so it's the exponential of a single connection to HL. So that's the full result. Now, it seems like that would be a very, very difficult sum to do, but it turns out that the sum of all of the diagrams obeys a simple recursion relation. So if I write this exponential, if I write f of z is log of v, so this is this exponential term. Yeah.
I'm confused about what you're doing. So I think in 2 dimensions, there has been some analysis of a conformal block for Virasoro, full Virasoro symmetry.
Yeah, exactly.
This is just a contribution of conformal block where intermediate states are identical.
Absolutely. This is the Virasoro identity.
This obeys the logic of the recursion relations, and
It does.
We know what, in certain cases, we can calculate it. So are you reinventing the wheel by doing this?
Absolutely not. So the homological recursion relations are just a recursion relation that you can only work out explicitly to like 6th or 8th order or so. I mean, you can type it in Mathematica. It's not a closed form analytic result. And I think before our work, no one had ever studied these heavy light limits. This is something where I'm just going to compute it exactly at large central charge in this limit.
Actually analyzing the Virasoro conformal.
Absolutely. So another way of saying exactly what I'm doing is I'm just computing the Virasoro conformal blocks explicitly in its limit.
Okay.
Yep. So if I consider this function, a very simple thing that you can observe is that if I take the second derivative with respect to z of f, then I have this power of z to the a1 plus a2 plus a3, and that nicely cancels these propagator factors. So there's a factor of just the sum of the a's and the sum of the a's plus 1. And if I take the second derivative of f, I eliminate these propagator factors, and I'm just left with this tree and this tree there. So in other words, I'm left with the product of this and that.
The derivative.
There is a minus sign missing. So if I write the correct okay
Exponents.
in my exponents.
How are you going to get a1 plus a2 plus a3 plus 1?
Good. So so formally you're right. You can write this for z times f and work it out. I'm just going to write for you the answer after you simplify this. So after you simplify this, you get a very simple recursion relation that just says that the second derivative is the first derivative squared plus 6h heavy over c divided by 1 minus z squared. So this is some simple differential recursion relation that the log of this v satisfies.
Relation. I call it a differential equation.
So it's a differential equation. The reason why I call it a recursion relation is that you can ask a much simpler question. How do you count all binary trees? The way that you try to count all binary trees is by the same argument except without these derivatives. And that gives you the generating function for the Kaplan numbers, which count these trees. So that's why I'm calling it a differential, because it would be a recursion relation if all you want to do is count the trees, but you want to actually get this function. OK, so you can solve this equation directly, and that gives you a formula for the Virasoro vacuum block. So in the remaining 3 minutes, let me just tell you briefly the other method, because it doesn't just give you the Virasoro vacuum block. It gives you any Virasoro heavy light block with any operator being exchanged. So instead of having the vacuum here, it would give you you can exchange anything you want along with all the Virasoro descendants, as long as the intermediate dimension is small compared to the central charge. So the other method, the idea behind it is very simple. So something you probably
Small compared to h light.
It doesn't have to be small compared to h light. H light and h intermediate can be anything as long as they're small compared to c. Yeah, exactly. So you may have heard that the energy momentum tensor isn't a primary state in 2D CFTs. A very explicit way of saying that is that if I perform a conformal transformation from the plane to some new coordinate system, W of z, then the energy momentum tensor doesn't transform like a primary. A primary would transform as to some t of this new coordinate, W of z. Times this thing called the Schwarzian derivative of z of w with respect to w. So this is the transformation law of a primary operator, but this shift is what makes the energy momentum tensor not a primary. And this shift has a very, very simple interpretation. If I think of my conformal transformation as putting me in a new metric, the stress energy tensor in a new metric can get a vacuum expectation value. This is exactly the vacuum expectation value of the stress energy tensor in that new background. So how can we use this? Well, the reason why this computation wasn't trivial was because we had H heavies upstairs, and those are just as big as C. So we had to work to all order in all of these various L's because we had factors of H over C coming every time. If H heavy had been small or 0, then we would only have kept the very first term in 1 over c, which would have just been a 1 Virasoro generator exchange, and we would have been done. So it turns out we can choose W to give us a new coordinate system with the same Virasoro algebra, but with respect to that new coordinate system, so we were expanding instead of in z and w, such that H heavy completely cancels. So in particular, if we choose W of z to just be 1 minus z to the square root of 1 minus 24 H heavy over c, then we find a cancellation between the Schwarzian derivative term and the naive primary transformation term such that the 3-point function of O heavy with the stress tensor completely, this H heavy piece completely cancels. And then this calculation becomes a very simple calculation in the new W coordinate system, and one can then use that calculation for any intermediate H, as long as it's small, to obtain the general Virasoro vacuum blocks. So I will not prevent you from going to lunch and end there and take questions.
I have 2 questions. One is that if I'm not mistaken, in the limit of large C and the limit you are taking, there are sort of conformal block actually approximated by review conformal. And the review conformal block actually can be computed by SL2C Chan-Simon theory, which is basically equivalent for this computation. So it seems like it's natural that for this sector you can reproduce gravity answer. Can I interpret what you have obtained in that way?
I certainly think you can. The first way that we computed, so there are three ways that I know of to compute this. The first way we computed it was very close to this Louisville method.
That recursion relation reminds me of the review equation.
Okay. Yeah. So it would be very interesting to understand how that directly corresponds. Yeah, you can interpret it that way.
The second question is that so you have shown that if you take this light cone limit, where z bar is 0 and z finite, then 4-point amplitude is dominated by the Virasoro descendant, assuming that there are no other chiral operators.
Yes.
What is the reason that that is a limit that is relevant for this program? So namely that you argued earlier that if there is a gravitational dual, then heavy light like 4-point amplitude, then you'd expect that light would probe the black hole geometry.
Yes.
And you wanted to reproduce the expectation.
Yes.
Now, what is the reason that we should be looking at the light cone limit in order to see this effect?
Good. So the light cone limit has a very simple interpretation in the bulk. As we were talking about in the first part, the light cone limit is what you use to understand these large spin operators. So in other words, light cone limit is associated with something orbiting around the black hole at large distance. That's why the twist bigger than 0 operators have decoupled, because you're very far away, and the higher twist things have forces that fall off exponentially with distance. So the reason why this is a way of probing the black hole is simply that you're staying far away, but you can still live in this correlation function long enough to see this thermal periodicity. So you can extract things like the Hawking temperature from this limit. Now that doesn't mean that the object, this O heavy, definitely has a temperature. It just means that if it has a temperature at all, it better be the temperature that we just computed. So for example, there's this regime of where there are these enigmatic black holes between like C/12 and C/6 in dimension. And we're not proving that those have a thermal interpretation, but we're saying that if it makes sense to think of them as a thermal state, then I think this has to be the temperature.
Thank you.
Any other questions?
So in the heavy light limit, the vacuum block is the same as the limit where you take the light operators to scale with C, but you work perturbatively in the ratio of that dimension to C to first order, right?
Yeah.
For the vacuum block specifically.
Yeah.
So in that limit, you can use the monodromy technique to derive the block, and sort of obeys a first order equation in terms of this accessory parameter.
Yeah.
So since you're just computing the vacuum block on the top board, can you not relate that differential equation directly to the differential equation you get in the monodromy problem?
So, I mean, we looked at that. This isn't identically the differential equation you get for the monodromy problem. So I'm not sure what to say about how to relate them. But I mean, it's a good question. It would be nice if there was some elegant way of understanding that. I mean, this is some differential. I mean, from a certain point of view, you could try to compute this also just in terms of bulk Feynman diagrams for the graviton or in some Chern-Simons description, and that's something we're trying to do. And I mean, this is some sort of recursion relation that the sum of all those diagrams have to satisfy. I'm not sure whether it has a connection to the accessory parameter story, but that was this first way of computing these blocks that I alluded to.
I have a question. So sure. In your heavy operators, you basically use their dimension.
Uh-huh.
How do you know that's the only thing that's coming up in those computations? There's not.
Good. So just the Ward identity, since these are Virasoro generators, the Ward identity for the stress tensor uniquely fixes the all of these matrix elements.
For one by one, I understand, but you have product of two, right? Product of two heavy on. I mean.
Yeah. Well, yeah. So this is heavy. So this is given by heavy some number of stress tensor correlators, and those are all fixed by the Ward identity.
So if you have two heavies, you have to take your OP, you get many chunks. You don't know what their dimensions are and anything about them.
Good. So what you're asking is why am I only keeping? So good. So what that's encoded by is the OP coefficients of heavy with something else. And that's actually what, so in the very last 5 minutes when I was talking about general Virasoro blocks, I was telling you how to compute this, but I have not fixed the OP coefficient of this intermediate guy with the heavy guys. I'm just fixing, once I know that OP coefficient, what the contributions of all of the Virasoro descendants are. So that's why these are the Virasoro.
These H that you're calling is the H which appears in the OP of those two big H's?
So good. So there is always a vacuum block, and that's just completely fixed. But then there will be some large set of other, presumably at large central charge, an infinite set of other conformal blocks that contribute. And in order to actually sum all of those contributions and get the full correlator, I would need to know all of those OP coefficients. So in other words, I would need to know all of the O heavy, O, H intermediate 3-point functions or OP coefficients. And I haven't told you that. I've just told you, once I know this 3-point coefficient, how I sum up.
You do not know if they are big or small. In other words, in the limit that you're taking z bar to 0, they could dominate, for all we know.
Oh, good. So they can't dominate in the limit that z bar goes to 0.
How do we know this?
Because they contribute, they start out contributing as z to the h, z bar to the h bar, and then.
Doesn't that depend on how many of these you have? All I'm trying to say is that you must be making an assumption of order of limits.
Good. So yeah. So one thing that we know is that from work of Slava, Chkov, and other people, that the OP converges in the Euclidean region. So I think we actually do know that because of those results on OP convergence, that that there isn't any order of limits problem. In other words, summing over h bar and taking z bar to 0 are. What?
Strictly 0, not
Yeah, so I can't tell you how small z bar has to be before these stop mattering, but I know that I know that there is a limit when z bar goes to 0.
Is that the dual gravity strictly probes z bar at 0, not small.
Oh,
It arises only when the issue is whether z bar is strictly 0 or not.
Good. I think I know for any theory that there's a z bar sufficiently small such that these make as small a contribution as you want.
Any other questions? Okay, if not, the sign share.